So time is up. Mash, do you want to take the lead and get started?
Sure. All right. So if everyone's ready, let's get right to it. I'm sure we're going to have a pretty interesting conversation. So I will begin going through the first part of our sections today, up to batch normalization. And then once we get there, Wencheng will take over for batch normalization. So as I go through this, I am by no means an expert. So I do welcome everyone jumping in. Feel free to interrupt me. I don't take it personally. Let's have a really good conversation. If you guys are, I'm sure there are many people here, hint, hint, my friend, the doctor, who understands the mathematics behind activation functions a lot better than I do. So please, let's get right to it. So continuing on from the last chapter where we started to understand activation functions and so on, and I'm sure we did discuss a little bit about the vanishing gradients problem, and that's where we begin today, with various types of activation functions. We get to a point, and if you can see my screen, I've got the book on the right and the Colab notebook on the left. And if anyone needs to get a copy of this Colab notebook to run on their own, I will post it both on the chat as well as on Slack. So please feel free to copy it. And so we'll run this side by side along with the book. What I also did, and this is going to be important if when others start to do the same thing, I restarted my kernel because I added some extra code, and you'll see that here. I want to make sure that we're getting a fresh graphs every time. So any questions up to this point? All right. So as we found, one of the things that happens with basic activation function. So let's create a very basic activation function, a logistic activation function right over here, 1 over 1 plus exponential of minus z. And we plot this out. As you can see, here's the curve. The vanishing gradients, the exploding gradients, here's a sense of it. At the higher extreme values, what happens is the curve concentrates, or in other words, saturates towards as it gets asymptotic. And that's the saturation effect that we're getting. This is not what we want, because we don't want for higher values of our training model where the activation function just gives you like a 0 or a 1 every time. And this is what we're trying to help resolve. And all of these brilliant researchers in this space try to do that. And so there were one of the seminal papers on this space, because there was sort of a lull in deep learning from the 1990s to about right before 2010, because they were beginning to observe something like this, where the saturation problem. They didn't know how to resolve it. And so we come along to this paper by Bengio and Glorot, where they said, well, we've got this problem. Here's a slightly different way that we feel you can improve it. What did they do exactly? Anyone know exactly what Bengio and Glorot said to do with their method of initializers?
Yeah, I'll talk a little bit on that when we get to the paper. As soon as you finish, there's some equations there, and they try to compare different initialization methods and explore the behavior of gradients and activation values based on different initialization methods. So we'll touch upon that.
Excellent. So in Keras, when we run, go ahead.
Yeah, sorry to disturb you. Actually, before we go on, based on this diagram, I just have one question. Assume we have an image data and we normalize generally before we feed it to the network. we normalize to 0, 1 or -1 to 1 range. So even if we normalize 0 to 1 or 1 to -1 to 1 range, and when you send that kind of normalized data to the feed forwarded network, maybe assume 1 or 2 layers. I mean, when you run through that kind of normalized data to the in one of kernel layers or dense layers, the output that we get, we apply activation, right? Still, I mean, how we can get which goes beyond this 0 and minus or 1, that range. So
That saturation problem.
Yeah.
That's exactly what we're going to begin to explore today. So there are separate things. It depends on how you initialize it. We're going to go into those equations momentarily. And here are some, but gradually walking towards your answer.
The initialization, it's a kind of kernel initialization that we are talking about, right? I mean, rather than randomly initializing, I mean, when you're these guys, they came up some approach to initialize kernel weights,
right,
so that
right,
I mean, training goes faster. But my question is,
that's
on
correct.
the input itself, we are normalizing before we feed it to the network. Still, sigmoid, when we apply sigmoid, it's how likely it gets saturated.
Good
So
question.
Can I just interject? I don't necessarily think that this sigmoid is it should be confusing you, because you can just as easily have a sigmoid, that is going to range from -1 to 1 on both axes. I think this is just a scaling thing that he's kind of trying to show by increasing the length of the area of saturation, so it doesn't all stack up on each other. You can adjust that. So I mean, I think that's, if you're getting hung up on that point, you shouldn't. Can I also interject as well? When this started out, from what I've read, the big problem is that nobody really knew what to do and how to initialize. So, people initialized at 0. Well, that didn't work. People initialized at 1. That didn't work. Then for a long time, they were initializing completely randomly. And that sort of worked, but it only worked if you got what was known as a lucky initialization. If your numbers kind of worked out so that your neural net would, output what you wanted, great. If not, you kind of bombed out and you said, well, let me try again. And there was lots of descriptions of, people in the initial years of deep networks, running the algorithms multiple times to be sure about their output. And, that's still an issue to this day for other reasons, but I've spoken on this before. All right.
If I can, hi everyone, if I can add anything to the first question, I think maybe it will become clear once we move forward and we talk about the vanishing gradients and exploding gradients. But to just answer your question, how it, I understand very well your question. You said, okay, we normalize, so how can it be, for example, outside the range of the 0 and 1, so forth. So actually, what we are really here concerned about is when you do your back propagation. So when you do your back propagation, the like you see, like where those arrows are pointing for the saturations. Yeah, you see. So those are going to be very almost like 0, right? And same way, okay, so those are going to be, and that's what's going to lead to our vanishing gradients. And so, for example, you said, and for exploding gradients, the exploding gradients, actually, they're going to be in the middle. They're going to come out exactly from right there. That's where from the derivative, because like we're working with the derivative of this function. And I think to answer your question, if you go and you try the back propagation for a single variable, for a single, like if you just have a single variable, a single feature, and you do the chain rule, the back propagation, and you can show, and you can see that, hey, it's vanishing right there and it's exploding right there, that would be great. But to answer your question, to just follow that up, again, we're adding all this eventually. Okay, eventually when we do the back propagation, we're adding all these terms together, and that's how this saturation will just end up. And that's how it's being saturated, because eventually it's not just like one thing. When we go back, we're adding the derivative of that activation function many with so many weights, and that's what's kind of, and I think that will become clear. I think it's just too early maybe for this question.
Yeah. So as you build it up in the code, if you look on the left, here's how you define and set this up. So you know your activation, say, is just going to be your basic ReLU function or any other choice, but the kernel initializer, so the question, here's how you can set it to HE normal, or even the fan that he talks about using, either the fan in or the fan average. Here's the parameters. You just put them in as you start, and so on. Actually, let's make sure we do it consistently with this one. So moving on, here is that Glorat talked about this in this way of doing the initialization, where you can do either that uniform or a normal distribution, and where, as far as I can understand, that's the mode that you put into Keras when you initialize it. Those factor in the choice of the activation function. This one little table here, table 11-1, gives you a sense, like if you're going to do different types of ReLU activations, then you should probably consider this, an HE initialization. But if you're going to do TANH or logistic or softmax activation functions, you should probably initialize with the Glorat initialization method.
Just FYI, I've never seen that before, and that's really awesome.
Mm-hmm. Can you go into little details, Stephen, why that makes it awesome? Like, where is that ability to be able to, where does it fine tune that Keras call? Where does it show up when it's actually working?
Well, I mean, it's going to just show up in, improved accuracy and an improved, result on your, whatever you're doing. Keras, kind of starts everything in, I believe, Hay initialization. If I'm not, no, sorry, it's Glorat initialization.
So it's
and
Glorat.
Yeah, no, it's Glorat. So I mean, and that's fine, but a lot of times we use residual networks, and certainly we have been initializing them frequently when we train from scratch on these networks with the Glorat initialization, and I have changed it to Hay on my own and had better results, but I really didn't know why. And now this is a pretty good explanation. I haven't really been experimenting with the Celu, and I certainly wouldn't have known to use the Laccoon unless I had seen it here. But when I do use the Celu in the future, I will use the Laccoon because it makes a lot of sense what he's talking about.
But I think it's purely based on the data distribution that you feed to the network. I mean, the data that you're feeding, I mean, especially for images, if you try to feed a complex scenes, then the different activation functions will work better compared to the sparse image data distribution that you can feed. So I think it varies based on the data distribution that you're feeding to the network.
Yeah, I have another comment that I'll share with you in a few secs, but I want Mash to be able to get through a little bit more of this, regarding, the comparison of ReLU and, these other variants, because there actually have been a number of papers that I've read, on some features of ReLU that are kind of interesting. And, relate to what we're talking here. And the basic summary is that a number of these papers may be bogus because of a mistaken assumption of what is actually going on. But I don't want to derail the conversation with that at this time. So that'll come in a little later, Mash.
Yeah,
thank you.
Sense.
So let's get right to it. So as we look at those activation functions, let's do it at the lowest level. We'll take a moment to try 3 different activation functions. We'll go with Leaky ReLU, ELU, the exponential, and the SELU, the CELU. That's the Jan LeCun one, I believe. So let's construct them and take a look at what they look like. So here's the Leaky ReLU. It's just taking, I found this interesting one on Wikipedia, of course, you gotta love Wikipedia. Here's the equation for Leaky ReLU. And what this does, it forces the function not to precisely go to a 0. And so let's do that where it chooses between that. We run it and let's plot it. And of course, here it is. So now, while it still goes up, on the other end for negative values, here's that leak. So it allows and begins to gradually allow a non-zero number. So now you've resolved the saturation for these lower negative values. Okay. So here is what you can use the different activation functions at this point. So of those activation functions that we're going to do, we're going to use Leaky ReLU and a few of these. So let's train the fashion MNIST model using this Leaky ReLU. All right, set it off, here, download beta. Now that it's loaded up, here's how we define that model, and let's go ahead and compile it. Okay, we're going to train, and our metric is going to be accuracy. And so just give it a few, about a minute or so, and it will run. It does run fairly quickly on Colab. Even on my own laptop, it was a little bit faster. And so what I added was, I want you guys to see the accuracy and the loss of this model. Ignore these graphs. We're going to get that for this specific model. Take a quick sip of coffee if you got it, or whatever your beverage of choice. We're almost there. So first, we're going to look at accuracy and the model's loss. And there we go. Here you can begin to see the train and validation. They're very close to one another, but they don't merge, they don't split away in different directions. And it's similar with the loss. Any comments up to this point?
Isn't it a bit odd that your validation accuracy is better than your train?
By chance, probabilistic, but it's not much better. We're going to see some fairly big differences. Let's go into the parameterized ReLU. Where does he explain that? This on page 335, he mentions the randomized Leaky ReLU, as Stephen had also mentioned, but this parametric Leaky ReLU, where alpha is authorized to be learned during the training instead of becoming a hyperparameter. And so that will perform better than these two graphs we just saw for the straightforward Leaky ReLU. So let's go ahead and run that and see if that's indeed the case. I wish I could have had this all saved up. I would have called it different names.
While that's running, I'm just going to make a quick comment. If you look at Geron on page 335, and Mash, if you said this, I apologize, but I didn't think I heard it. One of the things that's really relevant is this comment on the ReLU activation function not being perfect and having a number of the neurons die off, okay? And that means that they basically zero out and they're gone from the network. And, you know, in some ways, this could be considered a feature or a bug. And one of the interesting things is that there are quite a few papers back in 2017, 2018 that were talking about, you know, well, if you initialize the network, you know, the network kind of like, you know, what actually is functional within the network is actually a smaller subset of your deep net, and, you know, everything else is pretty much ignored by the network. Well, you know, if you're pruning everything, you know, by using a ReLU, yeah, that makes sense. And you know, one of the things that you may want to, you know, do, a lot of what we're trying to do with regularization in neural networks is actually forgetting. We're forgetting that individual, you know, data point so we can interpolate, and that interpolation then allows us to generalize, and that's the power of the neural network. So the ability to have a smaller neural network in a larger deep net is actually probably a good thing. You know, and conversely, one of the things that we were doing for a long time is, you know, using, you know, pre-training, you know, with transfer learning on ImageNet base to, you know, speed up our training and also to get better results. And, you know, the idea, and Jeremy has said this before, that, you know, what you do is you pick up on that part of the neural network that has already been exquisitely trained for a certain feature, and you use that, and you don't have to worry about the rest. So, you know, perhaps one of the things that we're doing with the ReLUs is pruning that away. Now, if we start using these other activation functions, you know, we may start waking up more of the neural network, and that may give us better results. And, you know, who knows what's going to happen with generalizability. But I think that point is pretty important. So, you know, you have to think about that when you're using the ReLU versus when you're using some of these other activation functions.
Yep. And here it is. So I need to make change in my code. I saved this new parameterized Leaky ReLU model as history 2. And so when you run that and look at its accuracy and its loss, this is distinctly different from the straight ReLU. It will perform differently. And as you can see over here, the validation is better than the train, but in a very disjointed way, right? Training was fairly smoother. Validation, clearly there's something unusual going on here. And same with the loss, it seems to go very differently across the epochs, and not quite of a smoother alignment with train. Do you guys see? So what if we were to do something a little differently? Let's change the initializers from HE normal, did I do it, to HE uniform. Let's really try to see if we can blow things up a bit. I will do this for model 2, model 2.fit. Oh, sorry. I'm really blowing this up. This is going to be a little more fun. Oops. This history 3.
Oh, well, let's run in. I can just add to
Yes,
what Stefan said about the die-in problem. I mean, what comes to my mind is pretty much just one thing or two things. So why does that happen? That really happens because we have this negative values, right? And what are those negative values coming from? Those negative values coming from that our activation is well, our outputs are negative, right? So our outputs are negative, and when would that happen? That, so like, if we think of like how we update the weight, right? We have this, the new weight is the old weight minus like the gradient times the learning rate. So sometime if the learning rate now is big, right? If the learning now is big, now we're gonna have like a big negative value that's gonna make the new weight negative, which gonna make that whole output negative. So actually having a large learning rate would certainly contribute to a dying ReLU problem. So actually, if we ever have we can see that there is a significant dying ReLU problem, that we have one thing that we can do, we can actually reduce the learning rate. And I hope that that makes sense if we just think of the equation of the update, how we update the gradients, right? So that's something that that came to my mind.
Thank you. Thank you, Salim. So moving on, as you can see, for this one, when we just made that slight change to uniform initializers, we're back to like a simple ReLU type performance. If you guys can see that, compare that with this, where the model was normal initializer, the HE initializer, just update that and you sort of correct some of it. Now, I'm going to move a little quickly. There is the ELU, the exponential LU unit, and that here is how you define it. We'll plot it. We're not really going to run that, but that's where you just pick the activation function keras. Let's move on to SELU. I guess it was not Jan LeCun's paper, but by Gunther Klumbauer, where he defines, and just go through just his code using SciPy. This is how it's defined. The equation's defined, and we call that. And so if you plot out the SELU, it will look like this, whereas you can see it'll expand out. Maybe we should try to have expanded out these the plot ranges. But if you set up all the parameters right, and then you call it and initialize it with that Jan LeCun normal initializer, I want to get us going again using fashion MNIST. Set this up. We're going to call this model, I don't know wherever we are, we'll just call it model 5, actually. And so where does, we'll take the same standards, we'll normalize and standardize the data set, and we shall call it model 5, but we'll only run it for 5 epochs. And I should have not overwritten this history file. I hope this still gives me the right history.
While you run that mesh, a couple of questions and clarifications. Answering Salim, your assumption would be that your old weight is always being positive, right? That's why you're saying if it's a large learning rate, then you'll end up with a negative. But that is an unfair assumption because you can use normalized data. Your kernel weights can be initialized to negative values. So you could basically start with a negative value as your old weight. So it's irrespective of what learning rate in that situation, right?
That's correct. Yes, that's correct. Yes.
Yeah, go on.
Question for you, Salim, and this is more of a pedagogical question. When you try to understand against all of the mathematics and the choices that go into creating these activation functions, your choice of initializers, if we wanted to get an intuitive sense, clearly this is important in a world where we begin to use deep learning more. What's the right way to approach it? We are, even in this session, I'm struggling to get us to move very, very fast. But if we could all slow down so that we could get a very strong intuitive understanding of the mathematics, what's the best way to do that?
For the math, I think this book does a good job. I mean, there isn't really too much math behind the activation functions. If you're talking about the activation functions,
it's just this.
Yeah, it's just different ones, and then eventually, when, for example, exactly when you don't use the exponential, that's great because you don't have all that extra compute. But you know, when you use the exponential, then it just adds compute. That's what I would think of.
Yeah, clearly, everybody, as you can see, each epoch is taking significantly longer than it did before because of the exponential. Where before it was 6 seconds, now the exponential has caused us to take it almost 5 times longer. And there we have it. As we can see, with the exponential, that same data set isn't performing quite as well in terms of the accuracy and the loss, not quite as smooth between the train and the validation. And so if we instead, for that same thing, if we go with, I hope this is going to work, we're going to still call it model and overwrite, and we're going to go back to ReLU at this point, train for 5 epochs. Hopefully we should get a much smoother accuracy and loss.
Thinking about Stephen's comment, I just wanted to pick his brain on. The reason, if you're trying to compare ReLU's dying out with a dropout, ReLU is going to be used literally after each convolutional layer or each dense layer. A dropout, in theory and in practice, is pretty much used towards the end of the network. So you're only dropping out towards the end of your network, which is kind of creating and helping in the regularization. But if you look at ReLU, it's used throughout in all the layers. And if you end up dying right in the beginning, you're not passing anything forward. Or the other way around, if you die towards the end too early, then you're not passing anything backwards in terms of gradients. So you basically have a huge model with a ton of stuff died out, which I don't know how much is that comparable to like regularization versus the network not updating itself.
Well, think about it this way. Okay? I mean, the way I think about that is that when I think about dropout, okay, you're forcibly knocking out a specific, node in the network. Okay, when you're using the ReLU and the node actually zeroes out, it's dead. It's never going to come back. In dropout, you're just taking it out temporarily and letting it fill up with a new value. Okay, so as you iterate, over that, you're going to get a different value. You're introducing randomness because the weights will fill in with a non-zero number. You would assume.
So this is for dropout, right?
Yeah, that's dropout. And I've seen dropout applied different ways. I mean, like initially, people were applying dropout like batch norm, like after every layer in a VGG type network, and that's kind of, less important. To be honest with you, I don't think really dropout is used very much anymore at all, if even. I think
Really?
I think it's an old kind of, it's an old style layer.
All fast AI networks.
No, I don't think.
I don't think that's true at all. I think
No.
dropout is a very important regularization technique, and it's even important in. You can use dropout to make an ordinary network into a Bayesian network.
Right.
So it's an important tool.
Okay, I might be wrong about that. I'm just saying, batch norm to me has kind of replaced dropout in a lot of applications that I've seen. It's.
I can add something there. I kind of agree at some points with Stefan there. I mean, but that being said, dropout is definitely like an effective regularization technique to prevent overfitting. But let's say, okay, what do we use nowadays? We mostly, if we use batch norm, we don't really use much dropout because, I mean, you can, but really it's kind of like redundant, So it's like you're just adding more without really a significant improvement, if no improvement at all. And okay, and
in theory, dropout, you're really not adding anything to the network at all, right? Your number of parameters or weights are not changing at all.
But exactly. But how are you doing that? You're adding this dropout masks, right? Which are you're adding these new matrices, which is the dropout masks, and that's how you kind of like you eliminate those you eliminate the nodes, and actually, so you're adding those masks, which means you're adding actually more multiplication, and that's how actually dropout.
I don't think you're adding a mask there, right? There is not a matrix multiplication that goes on to pick which neuron you're taking. In terms of like,
Don't you just randomly remove nodes from your network?
Right. So there's no math compute over there. I agree there is more math compute than a normal if there was no dropout, but I don't think it's a matrix multiplication or math that's going on there.
It's I mean, that's so let's check on that because that's definitely how I think, how I believe it's done, and I'm almost pretty sure that you do have a multiplication, and that's actually why dropout, if you notice, dropout would always will always make your training slower, because you do have these multiplications there. Yeah.
What my understanding of dropout is that dropout is like a knockout. So you're knocking out, like if you have think about a dense layer, right? You have 1,000 nodes in that dense layer, all right? And you're going to put a dropout algorithm of 0.5. So you're going to knock out 50% of those nodes in that layer, okay? And you're going to take whatever the weights are in that layer and throw them out, okay? And I honestly don't know. I don't recall whether they throw them out to 0, throw them out to 1, or throw them out to a random. I don't recall.
Yeah, exactly. That's exactly what's happened, Stefan. Just but exactly. But how do you do that? You do that by so, for example, you said the 0.5. For example, okay, so you're dropping out like 50%. How are you gonna drop out? So maybe like randomly. So
randomly.
So we have this mask that you kind of select 50%, and then you multiply it with the corresponding weights, and that's how those weights those nodes pretty much die out. You kill those nodes.
Yeah, I think conceptually you're right, Salim, but the real point is it's not, I mean, and yes, it would be slower, but if you were to compare a batch norm to a dropout, you would still probably end up with dropout being faster. But the two, in some sense, as we get into batch norm, you'll see that batch norm does something, at least from what we know now, and as our understanding is evolved, it does something completely different than what dropout attempts to do.
Yes.
Results,
I agree with you guys on that. I mean, batch norm is
they're different.
Well, the approach is that you just remember how we came upon batch norm, or how they introduce it. It's a technique to eliminate the problem of gradient explosion and vanishing gradients. That's a different problem. It's solving a different problem than dropout, which is solving a regularization, which is a regularization problem which prevents overfitting.
Exactly.
Though it does turn out that batch norm has regularization effects as well, but
right.
They're introduced for two different reasons.
Correct, exactly. And batch norm mathematically, as we'll see, it does involve more than just randomly shooting down a certain fraction of your weights as you move forward. So it's a little bit more complex than that, and that's the reason that I believe that batch norm calculations relatively to dropout will be more complex. But they, as Joseph said, target at least initial target or primary target is different for the two. There is secondary effect of that norm, as Joseph also points out, could also be regularization. So I've seen even in most modern networks on object segmentation and stuff that we saw even recently on Kaggle, like the most ones seem to use both batch norm or variants of norming with dropout. So I would agree with those who said dropout continues to be used in fairly modern, currently getting the best state-of-the-art results of many networks.
Yeah, but that's Kaggle.
If I want to mention something, maybe last in like 1 minute. So we talked about, and I really liked the addition of Joseph. I think he summarized it very well, like exactly like they're used differently. But for example, let's when do we use dropouts? I think they said like, when do we really use dropouts? And I think that's for example, and somebody else mentioned, oh, we use it on a VGG network. Let's just remember that when we really use the dropout, we usually just use dropout on the fully connected networks. I have not seen dropout anywhere used, for example, for the convolutional layers. So that's one thing. Also, like usually if we have a small data set, then usually regularization is not needed. So if we do have a small data set, then we don't need to use, for example, dropout also. Also, dropout, for example, of course, we need to wait. It starts like when we're training, it starts bad, but then over time, it gives us better convergence. So if we do that like early stopping when we train, if we limit our training, then we don't really, then we want to consider if we use dropout, we want to let it train all the way, right? So these are just and of course, and we don't usually place dropout at the last layer because we can't get the errors to update there.
Well, I mean, I'm just, I'll just mention that number one, okay, in Kaggle, the goal is to curve fit, okay? And any way you curve fit, okay, this unseen data set, okay, which is usually involved by ensembling and, figuring out how the heck you're going to get, the best result, that's how you win. That's point number one, okay? That doesn't necessarily reflect a real world application. That reflects, curve fitting a Kaggle data set. Number two, okay, I can show you Francois Cholet, okay, using dropout before every layer in a VGG type network back in 1997, okay? The rules weren't as well established, back then, and nobody really knew what they were doing with this stuff. And we still don't know.
Francois Cholet invented Keras, FYI.
But we still don't know. I mean, we still don't know. So I mean, like, that's why we try things. Some things work better. But but with batch norm is not perfect. I mean, I'm going to post, I'm going to post something for you guys, and it's different that I think you should be aware of. So it just. Just because you see it in Kaggle doesn't mean it's necessarily, it's good for Kaggle, but it's not necessarily applicable to your real world situation. You have to think about, what you're actually getting. Okay, I'm just stop there. I don't want to cause an argument.
That's true. I don't want to belabor the point, but I wasn't quoting just from Kaggle either. I was saying state-of-the-art results in multiple networks used for particular functions. So not just a Kaggle application.
No, I don't think Google uses dropout in their algos, guys. At least I can't recall seeing it recently.
Well,
yes,
without further ado,
you don't see dropouts much recently, but again, but it's just still a valid regularization effective technique for preventing overfitting. Yes, I agree with you, Sophie.
Now that I've introduced you guys to all the different activation layers. Here's Silu, does a little smoother. Here is one little comment before I hand over to Wencheng to go into batch normalization and go deeper into it. here's Geron's take. He gives this little thing: generalized CELU is better than ELU, which is better than Leaky ReLU and ReLU, and then of course better than TANH and logistic. So without further ado, Wencheng, do you want to take us right the guts of batch normalization and continue the discussion?
Yeah. Okay. So I was gonna share. Hold on. Let me take over the screen. So I was just gonna show one quick thing. There is actually this is the Fast AI CNN implementation, and there's dropout here, and this batch norm every single layer. So that's quick thing, and feel free to dig into more on the CNN learner of Fast AI. Cool. Okay, and also another quick thing. I think this paper I haven't happened to read it some time ago. I believe last year. Understanding difficulty of training deep feed-forward neural networks, and some of them. It is an old paper. It was written in 2009 or 2010. But it's quite interesting to be able to visualize like what's going on in terms of saturation. And this graph is the mean and standard deviation of activation values, output of the sigmoid during the supervised learning for the different hidden layers. So this is layer 1, layer 2, layer 3, layer 4, and layer 4 is this one, layer 1 is this one. And as you can see, the top hidden layer quickly saturates at 0. So slowing down all learning, but then slowly desaturates around epoch 100. So that's the layer 4. Yeah. So and again, y-axis is the activation value, and the x-axis is the epochs, how many epochs, and each epoch has 20,000 mini batch updates. And so it also mentions what they found, that's basically here. However, pushing the sigmoid outputs to 0 would bring them into saturation regime, which would prevent gradients to flow backward and prevent the lower layers from learning useful features. And I mentioned sigmoid is not good because it has non-zero means. And they compare this. So when we talk about initialization methodologies, in this paper, it was comparing this initialization methodology, which was a standard way of initialization, initializing your weights. But on the other hand, they developed their own initialization methods, which is this, using square root of 6, and n is layer size, and it went through a bunch of calculation and to derive that, and they call it normalized initialization. So this is what they meant by normalized initialization at that time. Now let me point to another graph that I came across. I thought there was these two sets of graphs are quite interesting as well. So let's quickly look at this. Backpropagated gradients normalized histograms with hyperbolic tangent activation with standard versus normalized initialization. Again, normalized initialization is this one, and the standardized initialization was the one that I previously mentioned. And look at how different these two graphs are in terms of backpropagated gradients. One, when you look at layer 1, right? So when you backpropagate to layer 1, the values or the variance becomes smaller. And whereas if you normalize, use normalized initialization, the backpropagated gradients, there's no decrease on that, and the variance, stays the same. Okay, and also same thing with activation value. Okay, that's what they found out. Comparing again standard initialization method and also normalized initialization method. So some very interesting findings, and this is definitely a paper that's quite fascinating. It's a famous paper, and I would encourage everyone to read it. Quite short paper too. So without further delay, let me just dive into batch norm. Did I close? Sorry, let me pull out my PDF. Okay. There you go. So batch normalization, and this again, like we discussed previously, this has been a quite popular way to normalize your layer, and we'll go through some equations as well. And so this was proposed by Sergey Ilf. I don't know how to pronounce his last name. Ilf. Okay. Christian
Ilf.
Yufa. Okay, great. In 2015, and they proposed a technique, and the technique consists of adding an operation in the model just before or after the activation function of each hidden layer. And this operation simply zero centers, and it normalizes each input, then scales and shifts the results using two new parameter vectors per layer. One for scaling, the other for shifting. In other words, the operation lets the model learn the optimal scale and mean of each of the layer's inputs. In many cases, if you add a BN layer as the very first layer of your neural network, you do not need to standardize your training set. So no more sklearn standard scalar for that. You just need batch norm. The BN layer will do it for you. Well, approximately, since it only looks at one batch at a time, and it can also rescale and shift each input feature. So let's go through some math. It's quite simple math, even though it looks a little complicated, but it's actually quite simple. This is just taking the main, and X is each input. Okay, just remember, X is each input, and you sum them up, and you divide it by the number of batch, and that's your mu, which is the mean. And again, mu b is the vector of input means evaluated over the whole mini batch B. It contains one mean per input. And I believe when he says input, it just means it's a vector. Okay. Yes, X, this is a vector of zero centered. Okay. And sigma B is the vector of input standard deviation. So this is just standard deviation, but square, and that's variance, right? So basically, and we've seen this equation throughout
This is just x minus your mean, and square that, sum that, divided by MB. So that's your variance. And if you square root of that, that's your standard deviation. Very simple math. And what's happening in this equation is you use x minus your mean divided by square root of your variance plus epsilon. I mean, again, this is just your standard deviation, right? If you take out the epsilon, the denominator is just your standard deviation. But we add epsilon because we want to avoid that if it goes to 0, then it screw up the whole calculation, because obviously your denominator cannot be 0. Okay, so, and then Z is basically using that and do element-wise multiplication with this parameter gamma. And this is trainable. Okay, so this and that are estimated, and this and your beta are trained. So, and this is just a simple linear operation. Then you get your Z as your output. Pretty simple math, nothing crazy. I want to stop here to answer any questions if there are any. Okay.
I was just going to ask really quickly. One of the big problems that I've always had with batch norm is the fact that it doesn't work so well at lower numbers. So if you have, you know, the M, which is the number of instances, you know, normally, you know, we will set that to 32, okay? But now pretend that you're going to set that to 4, all right? And I'm just looking at this and I'm thinking to myself, what is that going to actually really do to these equations? If we set M to 4 in both mu and sigma squared, so we're going to have X is the mean, right?
Mm-hmm.
So we're dividing a mean of 4 by 4 after summing. And we're taking the variance there, essentially.
X is the input, mu is the mean.
Okay, sorry.
Yeah.
So we have our 4 inputs. I don't know. Could someone help me work through this? And does someone see this more quickly than I do? Mathematically, when we look at this?
I mean, you can still do it for 4. It's fine. It's still gonna work. It's just it's not gonna be as good as if you have a mini batch with more, with you know, with like 50 or 100. You know, I think
Right.
I think the only one that you cannot do it is just for like a single one. That's just not you know, because you can't use the that's, but like for 4 you can still use it, but it's just not gonna work very well. That's all.
I'm thinking like,
and Stephen, you're right in this point that 4, or as you reduce the batch size, because you do it on a batch, it's less representative when we take it and use it for inference and stuff, and it's less representative of what the entire data set's norm, which is what we try to approximate with the batch, but we are all over the place if the batch size is reduced.
I'm just trying to think of it in my head, and I think that the second equation, the sigma squared equation, is where this comes in, because if you think about, you know, x sub I minus mu sub b, the likelihood is as you have more instances of x, you're going to have, you know, it's going to tend to a more central number, right? A more central mean that's going to be closer to that mu of b. So that, you know, x squared minus mu of b is going to be, I believe, reduced. All right. And
yeah, that's where you get infinity, right? Basically, you're saying if you have one sample, mu b is equal to xi.
yeah.
Then you do xi minus mu b, which is 0, and that 0 goes to the denominator, so you get infinity as that.
Yeah, but I'm just saying that if your variance is going to be increased in certain of the batches, you know, because you're not going to be having as large of a sample.
No, variance is going to be reduced, right? Not increased.
Well, it depends on the mini batch.
No, you're saying if you have lesser number of data points, your variance is going to be reduced, right?
No, I believe the variance is going to be increased if you have less data points.
If you compare across the mini batches, your variance will increase, reckon.
Yes. So that x minus mu squared term increases.
See, if you have one sample, we agree that will become 0, right?
Correct. So that when it goes in denominator, then it explodes, like somebody mentioned.
The variance is reduced if your mini batch size is small.
Right, but that's a special case. But I think that's a special case. If your mini batch, what if your mini batch size is 2? Okay, so if your mini batch size is 2, you could have either things that are very close to mu b or things that are very far away from mu b, right?
Mm-hmm.
So that square term could become extremely large or very small. And my argument would be with a mini batch of 32 or larger, that square term would tend to a more fixed value.
Yep. Okay. Anyone else wanted to say something? Okay.
I have a quick
I think
question.
if I understand what Stephen is saying is that the bigger the mini batches, the better. I think what I picked up on the last thing you said, which was that when the batch size is big, then the sigma b squared tends towards a more fixed value, and that's right, because the more data points you have in your batch, the better you're going to estimate the variance. The smaller the number of data points, your estimates of the variance are going to be different, and they're going to be more different from batch to batch than if you have larger batches. Then, as Stephen said, the estimates of the variance for each batch are going to be closer together.
And I think that what happens in the next term, with the square root, you're putting this kind of flipping around number in the bottom, okay? The sigma squared, and it could be very small, but it also could be very, very large. And your x minus mu is conversely also potentially large. So you're going to have a larger non-central tendency value of x hat. And when you do the element-wise multiplication, it doesn't really work so well. And that's why it screws up with no numbers. Okay, thank you very much. I'll write it down. Sorry.
Awesome, go ahead.
So I wanted to know, how do we calculate the mean and standard deviation during test time, like when we have just one example? So what do we do that in that case?
I think it mentions during training, BN standardizes inputs.
Okay, I didn't really read this.
You carry over the training values and use them.
And what about at test time? Well, it's not that simple indeed. We may need to make predictions for individual instances rather than for batches of instances. In this case, we have no way to compute each input's mean and standard deviation. Moreover, even if we do have a batch of instances, it may be too small, or the instances may not be independent and identically distributed. So computing statistics over the batch instances would be unreliable. One solution could be to wait until the end of training, then run the whole training set through the neural network and compute the mean and standard deviation of each input of the BN layer. These final input means and standard deviations could then be used instead of the batch input means and standard deviation when making predictions. Okay. So that's that. Does that answer your question, Gotham?
Yep.
Okay, great. So we talked extensively on this, and it's fairly easy calculation. So I don't need to go through each of them, each of the parameter again, and I just read through this. And I want to be cognizant of the time. Let me see if Joseph, do we have a hard stop at 3?
Yeah, more or less, yeah.
Yeah, okay. Well, we don't have much left. And but before I do that, before I end the session, and we can probably go through the last bit next time, but I just want to go through the code, and it's not much code, and just merely showing you how this was added, and it was also shown in the text as well. It's literally just adding batch normalization, calling that after each layer. And so that's that. And
well, it's interesting that in that example, if you could scroll up a minute, he does batch normalization once after the first layer, after the flatten, and he does that. And what he says is that he's doing that so that you don't have to do the standardization of the input data. That takes care of this standardizing the input data. But then subsequently, the batch norm is being run before the dense layer rather than before the activation rather than before the dense layer rather than after it.
Yeah, and I think he mentioned there's no right way of doing it, and people are still arguing whether you do it before or after. So before or after activation, actually, but that's what he mentioned, which is in this case. So batch norm, and he did it before the activation. Some people do it after activation. So, and let's see what FastAI does.
FastAI has a flag. You can set it either before or after activation.
But I think recently people mentioned that using after is more beneficial than before.
Right. If you think about what batch norm is trying to do, is you're trying to normalize the weight, right?
Before.
Trying to bring it down. So yeah, there's a flag there, Wenchang. You can either set it before or after. You're probably looking at a pre-trained network, so that depends on how the network was set up.
Yeah, yeah. So this was added before ReLU, and we did it before as well. Well, he did it before as well. So you know, very simple code. Again, that's one of the strengths of Keras, and it's just so intuitive and understandable in terms of adding layer, taking out a layer, and you know, setting the hidden units number, and with you know last layer softmax. Anyway, we had since we have a hard stop at 3 o'clock, and I think it's probably this is probably a good point